In the last lecture, we discussed isometries on the complex plane. Isometries were distance preserving complex valued functions which were defined on the entire complex plane. Throughout this course, we will be interested in studying complex valued functions which are defined on open connected subsets of the complex plane. So, we shall refer to open connected subsets of the complex plane by the word domain or region. We shall refer by domain or region. Both these words will mean the same thing, open connected subsets of C. Let's now look at function f from omega into C, where omega is a domain in C. So, let f from omega into C be a function, complex valued function, as you can see, defined on a domain or a region omega in C. So, when I say this, it means that omega is an open subset of C which is also connected, and f is a function on omega which takes values in the complex plane. For every z in omega, f of z is a complex number, and because of that, because of f of z being a complex number, we can define two further functions the moment we are given such a function. Define u of z to be the real part of f of z for z in omega, and v of z is defined to be the imaginary part of f of z for z in omega. Then we can write f as u of z plus I times v of z, which is sometimes captured by the expression f is equal to u plus iv. Let's look at some very basic examples, because we are going to study all types of such examples, but let's study the polynomials first, or rather let's look at the polynomials as the first example. Consider P from C to C given by P of z is equal to a0 plus a1z plus up to ad z to the power d. Notice that now we are not looking at this as a formal polynomial, rather we are looking at it as a function from C to itself. For every complex number z, we are looking at P of z, which is the complex number given by a0 plus a1 times z plus a2 times z square, adding it up to ad times z to the power d. Notice that the right hand side is a complex number. So, this is a polynomial in z, and because C can be identified with R2, we could also think of this as P of x comma y. Okay, since C can be identified with R2, we have z is say x plus iy, and thus P of x, P of z can be thought of as a polynomial in these two variables, and which is captured in P1 of xy plus I times P2 of xy. So, you can think of a polynomial in z as a polynomial in x of y with a real part and a imaginary part, both of which turn out to be polynomials with real coefficients. A thing to note here is that not every polynomial in xy can be realized as a polynomial in z, just z. So, for example, if p of x comma y is equal to just the first variable x, this is a polynomial in x comma y, but notice that if you write it in terms of z, then we have p of z is going to be equal to z plus z bar by 2. And this is not a polynomial just in z, there is a z bar featuring it. So you cannot write necessarily every polynomial in xy as a polynomial in z. That is to be kept in mind. We'll come back to all this again. So polynomials in z are a good class of examples we would be interested in. Another example would be of rational functions. Let's see. Let f of z be, or rather let p of z and q of z be polynomials which do not have a common factor, with no common factor, in particular no common zeros. And let's capture all the zeros of all the roots of the polynomial q, and let z of q be equal to the set of all those points in the complex plane such that q of z is equal to 0. Remember that q of z is a polynomial, it has a degree say d, then the number of points where q vanishes of counting multiplicities will be less than or equal to d. There cannot be more than d points in z of q. If we define omega to be the complement of z of q, notice that z of q is a closed set. Why? Because q is a continuous map and q inverse of a closed set will be a closed set, and therefore z of q is just q inverse of 0 and hence a closed set. And therefore c minus z of q is an open set in the complex plane. That means omega is an open subset of C. It's also not a difficult check to see that omega is a connected subset of C, because you are only removing finitely many points. It's very easy to show that any two points in C minus z of q can be connected by a path. The idea would be to get hold of a path in C which connects any 2 points, and then if it passes through one of these points in z of q, in a neighborhood of z of q, you perturb the path in such a manner that it avoids the point in z of q, and you can always construct one such path from a given point to another, and therefore this is going to be by the characterization of connectedness we have proved in the last week, a connected subset of C as well. Let me just say that open subset of C which is connected. Let's define R a function from omega into C given by R of z to be equal to P of z by Q of z. And such a function is called a rational function. These are also a class of functions which are of great interest. Such a function is called a rational function. We will next study some very specific functions which are of great importance and of great interest in the study of complex analysis. But before we come to that, let's also recall a few notions of convergence which are very essential in the study of these functions. The first one is that of uniform convergence. Let me not spend too much time. These are all notions which you would have already seen. Let me just give you a definition and go forward. So let omega be an open subset. Let omega be any subset. Let omega be contained in C, and f comma fn from omega into C be a collection of functions defined on omega. We say that the sequence Fn of functions converges uniformly to f if given an epsilon positive, there exists an n large enough such that Fn of x is close to f of x, epsilon close to f of x, irrespective of the point x. Let me write that down. We say that where the n is not dependent on x, that's what I meant when I said irrespective of the point x. So we say that Fn, the sequence Fn converges to f uniformly on omega if absolute value, if given epsilon positive, there exists some n in natural numbers such that the absolute value of Fn of x minus f of x is less than epsilon for all x in capital X and n greater than or equal to capital N. So this n does not depend on x, the point x, it just depends on epsilon. Given an epsilon, we have a capital N such that the distance of Fnx to f of x is less than epsilon for all x in, not x in omega. By the way, to define a uniform convergence, we didn't need to demand that omega is a subset of C. We could have defined uniform convergence on any metric space, complex valued functions on any metric space, we could have defined this. All the, I'll be assuming all the usual results that follow after the definition. For example, let me just note it as an exercise. If Fn's are a sequence, it's a sequence of continuous functions on omega which uniformly converges to a function, say f, on omega which converges uniformly to a function f on omega. Then let me rephrase it, let's start with a let. Then f is a continuous function on omega. This is that standard argument by using triangle inequality and splitting it into three terms picked in the right manner. We also have the standard Weierstrass M test, for example. If, for example, Fn is a function such that the mod of Fn of x is less than some mn for mn positive real numbers, and suppose for every x, and suppose summation mn is a series which converges, then the series summation Fn also converges. All those things do get carried forward here. I would also like to recall the notion of absolute convergence. We will discuss or recall the definition of absolute convergence of a series of complex numbers. So we say that a series summation Zn converges absolutely if the series summation absolute value of Zn converges. The word absolute is coming from here, n equal to 0 to infinity or 1 to infinity. It doesn't matter. Let me put 1 for consistency. Converges. It's a very strong notion of convergence in the sense that if a series converges absolutely, then the series itself converges, and not just normal convergence, it converges unconditionally. You look at any permutation of the series, it will still converge to the same limit. So this is a very strong notion of convergence. Let us next define a very important function in the study of complex analysis, namely the complex exponential. So complex exponential. In a course on real analysis, you would have seen the exponential function. Recall that x from r to r is the exponential function, is a function which is given by, whose Taylor series is given by summation x to the power n by n factorial. So let me just write that. Recall that the exponential, the real exponential x from r to itself is a function whose Taylor series is given by x of z, x of x is equal to summation x to the power n by n factorial, where n is from 0 to infinity. You would have seen that the real exponential is for every x in capital R, this series that is just written to the right hand side here, this is an absolutely convergent series. So x of x is absolutely convergent for every x in R. Let us define the complex exponential by mimicking this Taylor series expansion. Let's define it as a series which is very similar to this. Let us define the complex exponential yet again we will just call it x. X is now from C to itself given by x of z is defined to be summation n is equal to 0 to infinity z to the power n by n factorial. The fact that summation x to the power n by n factorial converges absolutely tells us that for every z, this series converges absolutely. For every z in C, x of z converges absolutely. That's something which we get for free from the theory developed on the real line. The exponential, the complex exponential also satisfies some properties which are very similar to the real exponential. So let me note it as an exercise to prove that the, okay, let us denote by e to the power z the exponential function. Let us denote by this shorthand notation. The function x of z. And the exercise is to show that e to the power z plus w is equal to e to the power z times e to the power w. So the proof is actually quite similar. It crucially uses the fact that the series e to the power z converges absolutely, and by an application of Merton's theorem, this tells us that e to the power z plus w is equal to e to the power z times e to the power w by considering the Cauchy product. Let us next study the trigonometric analogues of the trigonometric functions that is defined on the complex, on the real line. So again, next is trigonometric functions. Again, I'll start by recalling that the sine and cosine functions are given, have a Taylor series given by sine of x is equal to summation minus of 1 to the power n x to the power 2n plus 1 by 2n plus 1 factorial, where the series is from 0 to infinity. So this is basically the the Taylor series given by x by x minus x square x cubed by 3 factorial plus x to the power 5 by 5 factorial and so on. And we also have Taylor series expansion for the cosine function. Cos of x was basically 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial and so on. So basically this is summation n equal to 0 to infinity x minus 1 to the power n x to the power 2n by 2n factorial. Now let's look at the function exponential at the point ix. So e to the power ix is basically summation ix to the power n by n factorial, where n goes from 0 to infinity. And because this series is convergent unconditionally, we can write this as cos of x plus I times sine of x. If you write down the explicit form and gather the terms, you would see that this is equal to cos of x plus I times sine of x. And that's precisely, so this is for x in R. And this is precisely the collection of points on the unit circle that we had described in the previous lecture. So e to the power I theta, hence e to the power I theta for theta in R are points on the unit circle. Recall that any point on the unit circle, we do have some theta such that e to the power I theta is the point on the unit circle, and the set of all those thetas we captured as the argument of the point z. And for every such theta, e to the power I theta is equal to cos of theta plus I sine theta, which is a point on the unit circle. So these are the points on the unit circle which are written in the form of e to the power I times x, where x is in real numbers. The usual trigonometric properties tell us that e to the power 2 pi I is equal to 1. So this is for you to check that the straightforward checks actually. E to the power pi I is equal to minus 1, e to the power I times pi by 2 is equal to I, and so on. These are all directly trigonometric identities which you will already be familiar with. Also the product rule above tells us that this is the product of two such points, e to the power I theta and e to the power I phi, is going to be e to the power I theta plus phi. This is exactly the same thing which we had seen earlier in the last lecture. This is basically cos theta plus I sine theta, this is cos phi plus I sine phi, and this is cos of theta plus phi plus I times sine of theta plus phi. Also, the conjugate of e to the power I theta, you should sit down and check that this is equal to e to the power minus I theta. All these are exercises which you should sit and solve. Right, with this, let us now try to describe the sine and cosine functions in terms of the complex exponential. So notice that the cosine function happens to be the real part of e to the power I theta, right, or e to the power ix. So notice that cos of x, and how did we define the real part? It was z plus z bar by 2. This is going to be e to the power ix, this complex number, plus the conjugate, which is going to be e to the power minus of ix by 2. And similarly, sine of x is equal to e to the power, this is the imaginary part, so this is e to the power ix minus e to the power minus of ix by 2 times I. So notice that this is a function from R to R, and let's define the complex trigonometric functions cos and sine by using the same formula. So let us now define the complex trigonometric functions. Sine from C to itself and cos from C to itself given by sine of, let me start with cos of z. Cos of z is equal to e to the power iz plus e to the power minus of iz by 2. And sine of z is defined as e to the power iz minus e to the power minus iz by 2i. This is basically the formula for the imaginary part. The complex trigonometric functions satisfy the similar algebraic properties as the real trigonometric functions. So for example, it's a good exercise to sit and check that sine square z plus, or rather let me write cos square z plus sine square z is equal to 1. That's just straightforward. You just have to plug in the formula above and check that it does get satisfied. Although the algebraic properties of the real trigonometric functions do carry forward to the complex trigonometric functions, I should mention here that the geometric properties do not carry forward in terms of angles and such things. Along the same lines as trigonometric functions, one could also define the hyperbolic trigonometric functions. Let me just define them directly. Hyperbolic trigonometric functions. So let's define the hyperbolic trigonometric functions cos h from C to C and sine h, the hyperbolic sine and the hyperbolic cos from C to C given by sine h of, I should start with cos h of z. Cos h of z is just equal to e to the power z plus e to the power minus z by 2. Let us now see how the hyperbolic sine and the hyperbolic cosine are related to the complex sine and the complex cosine function we just defined. So to do that, let's consider cos of iz. Let's see how the function cos of iz behaves. This is going to be equal to e to the power iz I times iz, right? So this is going to be e to the power minus of z plus e to the power z by 2, and this is precisely equal to cos h of z. And how about sine I of z? Sine I z will be e to the power minus z minus e to the power z by 2 times I, which is basically equal to minus of I times sine h of z. So sine h of z, oh no, there is no minus here. Sine h of z is basically equal to minus of I times sine of iz. I have freely used the fact that I square is equal to minus 1. So if you carefully notice, I hope I have not made a mistake. Let's see. Yeah, that's right. So the hyperbolic sine is obtained by some rotations of 90 degrees because of the multiplication by I. When you multiply by I, it's basically rotations by 90 degrees. So the sine and cosine, the sine is related to the hyperbolic sine by some rotations of 90 degrees. The hyperbolic cosine is related to the cosine function again by some rotations of 90 degrees. The hyperbolic sine and cosine functions also have an analog of all the algebraic properties that the complex sine and the complex cosine functions satisfy. For example, so this is again an exercise. Check that cos h square z minus sine h square z is equal to 1. Right. So the complex exponential forms that right framework which integrates the trigonometric functions, the hyperbolic trigonometric functions, the real exponential functions. It's helping us give a very coherent theory. So let me stop this lecture here.